Yeah, thank you, Jeremy, for introduction. So I will first of all have a short introduction thing, and then I will give the heartbeat to Bing to talk about technical bit. So the reason why we want to do a presentation here is that we want to, because I mentioned about the AI part of the network. So all of the fantastic call you mentioned about the point of care analysis and remote a lot more engineering lab tests, but now we are thinking about bringing some example that we have done together with Royal Berkshire Hospital together, see how we use the real world data to provide the clinical decision support for the clinicians. And we're quite excited because we just had a human and machine trial together for our machine learning model. And we're really looking at the heterogeneous data that have different modality, and how can we use the blood test result data together with the electronic health record, and then to provide the additional support at the point of the care. So when I say at the point of care, it could be at the point of triage, at the point of referral, and also point of decision making of diagnostic as well. So so this is our team. So we have the project clinical driven and driven by the Royal Berkshire Hospital, and we have a good team of clinicians, Tony Bello and Tony Chan here, and Tobias, who is really looking into clinical and informatics stuff. And Bing is he has been leading the modeling and the data science bit of the research. We did all the hard work up here, and we play a small role in the whole team. So we have been doing several projects around the clinical care application, and our method is not just looking at one source of data, but we are really looking at a different source of data, because when the clinician doing the clinical decision making, so you are looking at not like blood testing data, you're looking at clinical notes, you also look at GP referral letters, and you look at the image as well. So it is actually quite a different modality of the data, and you want to make a decision out of those data. So, and especially when we have a real world data, so they always come up with a slightly more messy format. So there are missing values and the different modality. How can you fuse this information together, extract information together, using right information to provide the right decision support? So that is a kind of the real world challenges we are looking at. And especially if we go back to the future blood testing, so we have been talking about, we want to have a more quick decision support, decision making, but at the point of decision support making, sometimes you only have a very limited amount of data. How can you use AI that to provide accurate decision support within this real world data? So that is a challenge we are looking at. So we have been using the different data fusion strategies and also prediction strategies in the healthcare application, in the risk stratification, phenotyping, and really looking into a step forward, more multimodal, explainable AI. So provide as much transparency as possible to bring more trust for the clinician to the model, and also to provide real explanation, right explanation of the predictions that we have been doing. And the reason why we select elective care triage from elective care to secondary care is really inspired by our clinical team and Tony Chan here. So we most of the time, especially for disease, for example, inflammatory arthritis, where the symptoms not very specific, and also there isn't any single biomarker to tell, okay, this is a biomarker for the disease, then we will need to use quite a lot of different type of data to help to make a decision. And the problem comes when the GP referral, when GP thinks a patient will maybe a suspected patient for inflammatory arthritis, and then they will refer it to the secondary care hospital. But because of the non-specific symptoms, so the referral not always accurate. So for example, from the data, so only 40% of referrals is proven to be the right referral, which means that the inflammatory people are really entering the early inflammatory pathways at secondary hospital. So only 40% of them are assessed correctly. So that brings more work for the clinician. I think Tony knows much more than me. So they will look at, they have to assess referral again of the from the GP and then make assessment. She sees which ones might have inflammatory arthritis and which ones might have non-inflammatory conditions. So they will go to different pathways during the clinic to book the clinical appointment. So this actually takes quite a lot of time for the clinicians, especially everyone's quite busy and in the clinical activities. So then we, our clinical team have come up with really brilliant ideas looking at how can we use machine learning to streamline the process, especially the process here in the assessment shows how can we streamline the assessment if the patient may have the inflammatory or not, and if yes, what is the risk? How do we stratify them? So that is the background of it. But now the challenge is that we have different data. So in the process of the referral, we have GP referral letters and test data. That means there's a heterogeneous data, it's multimodal data. So how can we combine them and into a real world decision support system? So that's the AI challenge we are facing. And then I will hand it over to Bing, who did the hard work of the modeling, to tell you more details.
Okay, many thanks, Vicky, for the so detailed introduction about the multimodal machine learning in the healthcare domain applications. Next, I will cover the methodological parts of our previous research about the primary care to secondary care referral triage. And in the real-world referral processes, the data source are multimodal. So as the figure 1 and the figure 2 here shows, the figure 1 is the example of the GP referral letter, and the figure 2 is a part of the blood test results. And before diving to the machine learning part, a very important question is that we must understand how a physician makes assessment based on two kinds of data for a referral triage. And based on our preliminary study, we found that the physician makes the assessment from 3 points. The first point is to go through the GP referral letters and refine the structural information from the GP referral letters, such as key medical symptoms or the relationships between the different symptoms and the history of these patients. And the second one is to go through the GP blood test results data and identify some indicators from the blood test results data. And third one is to give the final referral assessment outcome based on the information extracted from the GP referral letters and the indicators from the blood test results data. And similar to this real-world assessment process finished by the physician, we would like to build a machine learning model to do the same thing. We have 3 challenges faced. The first one and the second one is to build the machine learning models separately to extract information, the feature representations for different kinds of data sets, such as the GP referral letters and the blood test results data here. And the third one is to fuse the different feature representations or the data modalities, or maybe the models predictions from different separate models we mentioned about here. And this is the whole architecture we proposed in our research to for the purpose of the referral triage. And the inputs of this architecture is the GP referral letters here, which is unstructured test-based data. And another part of the input data is the blood test results data from the data warehouse. And the output of this model is the classification output of the specific patient. That is whether this patient has inflammatory arthritis or the non-inflammatory conditions. And our model consists of 3 submodels: the blood test results model, and the GP referral letter model, and the hybrid model. The hybrid model will guess the we'll get the predictions from different separate models and combine them together to get the final output for the specific patient. And this is the NLP model we proposed in our study to classify patients having GP proliters. We have some challenge here for this kind of research, such as that we have very limited data in our research scenario, especially on these 332 inflammatory arthritis patients. So we introduced the two kinds of data augmentation methods here, including the EDA and the back translation, hoping to unleash the full power of the performance of the different models we developed here in our study. And another challenge is to extract multi-level information contained in the GP-prime letters. Because as we know, the different parts, different layers of the original bird model could be able to identify and extract information from different levels, such as the low layers of the network could be able to identify the freeze level information of features from the test data, and the intermediate layers of the network could detect some linguistic features, and the top layers of the network can identify the semantic feature from the test data. So in our research, we dynamically fuse the different level information extracted from by the original BERT model and made some slight modification to get a better feature representation of the GP from letters. And the table 1 is the comparison results with 95% CI of the 5-fold consolidation. And it's apparent that the Amber model we used comprehensively outperforms the BERT model here in almost all metrics. But it is disappointing that the data augmentation methods here can hardly contribute to the final performance gain. And the Amber model we developed here without the data augmentation achieves the best performance in almost all metrics here. And besides, we also compare different transfer learning based fine-tuning strategies of BERT model, Amber model on baseline data set. It's also very disappointing that the different fine-tuning strategies can hardly contribute the final performance gains, such as gradual unfreezing and layer-wise learning. And this part is the machine learning models we developed to classify patients having blood test results data. Similar as the NLP-based model, we also introduced the two kinds of data augmentation methods here to hoping to make the data set looks much larger. And another challenge is the data missing for some patients. So we use the two kinds of imputation methods to impute the missing data contained in the patient's blood test records. And we exhausted the 6 kinds of machine learning models and finally found that the LGBI model consistently outperforms the other kinds of machine learning models by using multivariate imputation and the no subsampling method applied. And besides, the global interpretability results also identify some important blood test indicators contributing to the final classification of the patient. As the figure 1 shown here, the rheumatoid factor is a very important feature for the model to make the final assessment. Okay, this part is the probabilistic fusion and the architecture fusion methods we proposed in our research. And because we have the heterogeneous problem of the source data site, so we must fuse the different predictions of different models, or maybe the feature representations from different submodels to get the final outputs of the specific patients. And for the probability fusion, as the algorithm 1 showing, we have 8 fusion steps here, and the fusion weights of different models are calculated based on the standardized G-mean weight or the standardized AUC weight. And in the real world application scenario, for patients having both GP referral letters or the blood test results data, we will use this algorithm to fuse the different predictions from different models. But for the patients having either blood test results data or the GP referral letters, we will output the previous model's prediction directly rather than using this algorithm. And for the architecture fusion, the convergence rates of different submodels, the substructures of the multimodal networks are various. So it is very tricky for us to train this kind of networks simultaneously. In order to tackle this problem, we used a well-trained AMBER model we have mentioned before in the LP model part. And we will freeze all the parameters of the AMBER model and only update and train the rest of the parameters in this network based on the 119 patients data set. And this part is the result of the probability fusion and architecture fusion. The table 1 shows that the probability fusion technique is better than the single models in all metrics, and table 2 shows that the probability fusion strategy is better than architecture fusion for almost all the metrics. And another very important question for us to make the predictions by different models trusted by the clinicians, and the transparency and trust problem is very important to us because there is a contradiction between the data scientists and the clinicians. In order to help the clinicians understand the model's predictions, so in our research, we have some challenge to identify the keywords in the GP referral letters and contribute to the final classification and rank the blood test results according to the feature importance, and finally give the final risk probability having IA or NIC. And the AMBER model and the table figure 1 and figure 2 are an example of Lyme interpretation of the triage representation of inflammatory arthritis patient. The final ensemble risk probability is 0.73 having IA. And the AMBER model shows ability to identify some keywords in the GP referral letters. And the table 2 shows that our model could be able to identify some key indicators or key blood test items and rank them by the feature importance here. And this part is the decision support system demo we co-developed with the clinicians from the RBH Trust. And the figure 1 shows the real-time risk stratification of referrals waiting to be triaged through the decision support system. And our model will give a ranking of the patients in the waiting list by the risk probability. And the clinicians could choose to have a look or check the high risk level patient at first and the lower risk level patient later. And if the clinician choose a specific patient in this system, and the pop-up window will visualize the detailed predictions with explainable results like the figure 2 shows here. And this patient has risk probability of 0.71 probability to get the IA. And the left part is the GP referral letters with explainable results. And the right part is the blood test items ranked by the feature importance. Okay, that's all the technical parts of our previous research, and now back to Vicky to continue to the next part.
Yeah, I just want to finish the final part of our recent work over the summer, so I'll quickly go through that. So being mentioned the digital support system, and now I want to refer back to previous presentation, we do see quite a lot of infrastructure, digital readiness. Looking at, for example, some GP referral letter might not be machine readable. So if we want to fully automate the digital support system, there's still some time to go. So we need to make sure when all the GP referral letters and the things that are readily machine readable. But we really keen to test how compare the model performance and human performance clinicians. So we have done a manual testing, manual trial with Royal Berkshire Hospital, and then we have selected 88 patients, including 22 non-inflammatory and 26 inflammatory patients, and then we use a model to predict, using a model to calculate the probability of the disease based on the GP referral letter and the blood test at the point of the referral. And also we compared with the clinician's assessment and using the final diagnosis as a ground truth to compare the predictions. So we found that we use the data deliberately, use the patient that have a more comprehensive data without missing data. So if we're going to use a patient without missing value, our model works very well. So almost comparable with clinicians. So with all the metrics above 80% of precision, recall, accuracy, F-score, and also G-means. So that's a quite exciting, shows promising direction, saying that there is a potential that machine learning could be used in the field. Of course, we need to, there's a work in progress, we need to do more experiment. And also the number shows that it's slightly better than the manual clinical criteria. So according to the literature and talking to the clinicians. And also it is estimated by talking to a clinician and also with Tony Chen is that with this support, it could potentially reduce quite a lot of time for clinicians assessing the referrals, because what we can do is that very quickly, we can prioritize the patients from high risk to low risk, and also give the key information in the right quick way, so that can save some time for the referral assessment. So that's all for this small case study, but we still have still work in progress. And what the message we want to convey is that although we're talking about data, AI in the future blood testing, I think quite important thing is that how can we make full use of the blood test data with other data around the patient, and then to better support the clinical decision making in the real world healthcare. So that's all. Thank you very much.